So for the day 8 notes, it's going to be our second day on the chain rule. So essentially today we're going to look at a few more examples of using the chain rule, some of them with other differentiation rules also. So at times you'll have to use the chain rule to complete a product rule or use the quotient rule inside of a chain rule. So it's just a combination of the derivative rules we've talked about thus far, and depending on the function will determine kind of how we're going to approach it. So if you look at example 1a, here are my options here. If I want to take the derivative of that function f of x, I could multiply 4 minus 9x to the fourth all out, distribute the 3, and then have a polynomial. And then I could just use the power rule for every term, and that would be my derivative. So that's an option. The other option is, which would be the better option, is to apply the chain rule. So the setup would be 3 times the derivative of 4 minus 9x to the fourth. Now you may not need to write this step, but I like to, at least at the beginning, to just emphasize that 3 out front is not going to affect how we take the derivative, and then to complete the derivative of 4 minus 9x to the fourth is going to require the chain rule. So f prime of x would be 3 times, and then the derivative of 4 minus 9x to the fourth will be 4 times 4 minus 9x to the third times the derivative of 4 minus 9x. And again, if you remember the pattern or the setup of the chain rule, it's really used to take the derivative of a composition of functions. So in this case, the idea there is 4 minus 9x is a function of x, all being raised to the fourth. So to take the derivative, it would be like using the power rule here, so 4 times that quantity to the third, leaving that quantity untouched, so 4 minus 9x stays 4 minus 9x in the first part, and then I'll take the derivative of that interior piece. So that's what the chain rule is, essentially. It's the derivative of the outside with the inside untouched times the derivative of the inside, which in this case is 4 minus 9x. So to finish that, I would get 3 times 4 times the quantity 4 minus 9x to the third times the derivative of 4 minus 9x, which is negative 9. And all I would do at this point, again, differentiation is done, is I would just maybe simplify the derivative. And what I'd get is negative 108 times 4 minus 9x to the third. So that's how we would approach that instead of trying to multiply this all out and get one long polynomial to take the derivative of. For example 1b, what you'll notice is I have x plus 8 to the fourth times 2 minus 3x to the seventh. That is a product. So to take the derivative, I would set up the product rule. So the derivative of g prime of x is going to be x plus 8 to the fourth times the derivative of 2 minus 3x to the seventh plus 2 minus 3x to the seventh times the derivative of x plus 8 to the fourth. So that is the setup for the product rule. And what you'll notice is to take the derivative in each part of the product rule is going to require the chain rule, because I have some quantity raised to the seventh power, and that quantity isn't just an x or a y or a b or an a. It is a function of x. So what the derivative is going to be is x plus 8 to the fourth times, and then the derivative of 2 minus 3x to the seventh would be 7 times 2 minus 3x to the sixth. So applying the power rule there, leaving the inside alone, times the derivative of the inside, which the derivative of 2 minus 3x is negative 3. So to take the derivative of 2 minus 3x to the seventh requires the chain rule, and it would be 7 times that inside piece to the sixth, leaving that inside piece untouched, times the derivative of the inside, which is what the chain rule is, plus 2 minus 3x to the seventh, and then to take the derivative of x plus 8 to the fourth, it's 4 times x plus 8, left alone, to the third, times the derivative of x plus 8, which is 1. So as we walk through this, right, I'm not going to write d dx of every piece all the way through, but that's essentially what's happening. You cannot forget to take the derivative of the inside as you work through your chain rule. So I could clean this up here a little bit, and I will. So the derivative will be x plus 8 to the fourth times 7 times negative 3. So I'm going to call that negative 21 x plus 8 to the fourth times 2 minus 3x to the sixth. And then the second piece would simplify into 4 times 2 minus 3x to the seventh, x plus 8 to the third. So you could go a little further and factor out any of the common factors, but for now I'm going to leave it like this. Only if I were to solve it would I probably go a little further, so that's what I would call my derivative there. For C, what you should hopefully recognize is I have a quotient all being raised to the second power. So my options here are square the top, square the bottom, and get a polynomial on the top and a polynomial on the bottom, and then use the quotient rule. That would be kind of alleviating your need for the chain rule. Or what I'm going to do is think of this as, some quotient raised to the second and use the chain rule. So what I'm going to call this is dy dx is going to be 2 times that inside untouched to the first times the derivative of the inside. So my notation is going to be d dx of that interior quotient. So I haven't taken the derivative of that inside yet. To do so will require the chain rule. So what I'm going to do next is actually take the derivative of that quotient. So I'm going to get 2 times x plus 5 over x squared plus 2 times, and then to take the derivative of that quotient is going to require the quotient rule. So the bottom, x squared plus 2 times the derivative of the top, which is the derivative of x plus 5 is 1, minus the top times the derivative of the bottom, all over the bottom squared. So the interior part of that quantity to take the derivative required the quotient rule. So from here I'm going to do no more differentiation. The derivative part is done. I'm just going to clean it up a little bit. So what I'm going to call this is 2 times x plus 5 over x squared plus 2. And then I can write that second fraction all as a single polynomial up top. So distribute the 2x and the negative, and you should get negative x squared minus 10x plus 2. So the last thing I would do is write it as a single fraction. Notice multiplying, across the top and across the bottom should give me dy dx equals 2 times x plus 5 times negative x squared minus 10x plus 2 all over x squared plus 2 quantity cubed. Because I had one of those quantities, x squared plus 2 in the bottom in one fraction and 2 of them in the other fraction. So that's how I would simplify that. It would make solving a lot easier if I were to say have to set that equal to 0 and make a chart to figure out where the function's increasing or decreasing, because that's the type of stuff we still need to know how to do. All we've really done with the chain rule is opened up the types of functions we can take the derivatives of and then continue to answer the same questions that we've been doing. So for example 1D, hopefully you'll notice that this is a product, so e to the 5x times the square root of 4 to the x plus x cubed. So I'm going to set up a product rule, and then within the product rule I'm going to have to use the chain rule. So it might be helpful to rewrite the function z equals and call the 4 to the x plus x cubed something raised to the 1/2 power rather than a radical. So the setup for the product rule, and notationally I'm going to use dz dx because my function was z equals. You could also call that z prime. Those would be equivalent notations as well, as long as you know you're taking the derivative of a function with respect to x. So the setup would be e to the 5x times the derivative of that radical part plus that radical part times the derivative of e to the 5x. So that is, again, super explicit setup for the product rule. I haven't taken any derivatives yet, but when I do so, this will be dz dx or z prime. So to take the derivative of 4 to the x plus x cubed to the 1/2 will require the chain rule, and to take the derivative of e to the 5x will require the chain rule. So e to the 5x times, and then the derivative of that radical part will be, pause it there, 1/2 times 4 to the x plus x cubed to the negative 1/2. So again, it's some quantity raised to the 1/2 power. So it's going to be 1/2 times that quantity to the negative 1/2 using the power rule, leaving the inside alone, times the derivative of 4 to the x plus x cubed. So the derivative of 4 to the x is 4 to the x times ln of 4, plus the derivative of x cubed is 3x squared. So all that in purple in that second line of mine is the derivative of the radical part, plus 4 to the x plus x cubed to the 1/2 times the derivative of e to the 5x. And the derivative of e to the 5x would be e to the 5x times the derivative of 5x, because 5x is technically our interior function because it's e to some function other than x. So all I would do here is just clean this up. I'm done taking the derivative. I used the chain rule in both parts. So what I'd write is that 1/2 4 to the x plus x cubed to the negative 1/2 can all move to the bottom. So that becomes 2 in the bottom, and 4 to the x plus x cubed to the positive 1/2 in the denominator, and then all I'll do to the second part is just call that 5e to the 5x times 4 to the x plus x cubed to the 1/2. I would stop there unless I had to solve that or maybe wanted to write them as a single fraction and get common denominators, but again, as long as I'm going to require you just to deal with any negative exponents you have and then essentially stop from there unless we had to actually go further and solve. So the chain rule happened inside of a product rule in that case. What made that one a little tricky is, again, we had a radical piece with an exponential inside of it, so it's really encompassing all of the derivative stuff that we've learned so far. Power rule, product rule, and then chain rule. The only thing that's missing is a quotient in that one. For example 2, we're asked to determine if a function 1/9 times 3x plus 1 quantity cubed is concave up or concave down. So what I would want you to be thinking at this point is, what does concave up and concave down mean? So concave up would be the second derivative is positive or the second derivative is negative for concave down. And again, it would be specifically at whatever x value you're asking you to find. Now, you could be asked, determine where this function is concave up or down, and that would be going through the process of making a chart. But if it's just asking concave up or concave down at a specific x value, you just need to plug that x value into your second derivative and determine if you get a positive or negative number, and that should tell you whether you have a concave, if the function is concave up or concave down at, in this case, 1. So obviously, in order to plug a number into the second derivative, I need to find the second derivative. So the first derivative would be 1/9 and then times the derivative of 3x plus 1 cubed. You don't have to write that step. I like to, or at least want to have you thinking that 1/9 is out front. It's a coefficient. Some students will want to use the product rule here because they see like 1/9 times something else. But again, a coefficient out front is just a scalar. It's not going to affect how you take the derivative of that 3x plus 1 quantity cubed. So the first derivative is going to be 1/9 times, and then the derivative of 3x plus 1 quantity cubed will require the chain rule. So it'll be 3 times 3x plus 1 quantity squared, leaving the inside alone, times the derivative of 3x plus 1, which is 3. So I can simplify this. I have 1/9 times 3, which is 1. So I end up with 3x plus 1 quantity squared as my first derivative. So again, use the chain rule, simplified fairly nicely. So to take the derivative of this function, h prime of x, I'm going to use the chain rule again. So the second derivative is going to be 2 times 3x plus 1 to the first, applying the chain rule again. So 2 times the inside untouched to the first, times the derivative of 3x plus 1, which is 3. So what I get for h double prime of x is 6 times the quantity 3x plus 1. And now what I need to determine is the first derivative positive or negative at 1? So I'm going to plug in 1 into my second derivative, and what you should get is 24. So h double prime of 1 is 24. So if h double prime of 1 is positive, what that means is h of x is concave up at x equals 1, and my reasoning would be, since the second derivative is positive there, and the easiest way to write that is h double prime of 1 is greater than 0. So still answering the same types of questions. The only difference is to take the derivative will require at times the chain rule, which is what we're practicing here. For example 3, we are going to find the equation of a tangent line to a couple functions at a specific x value. So a couple things to remember about the equation of the tangent line. We're trying to write a linear equation, right? It's a line that's tangent to a function. So the two things you need are the slope of the tangent line and the point where the line is tangent to the function. So finding the slope of the tangent line is taking the derivative and plugging in a specific x value. So I'm going to have to take the derivative of f of x and plug in 4. And what that'll give me is the slope of the tangent line, and then I'll also need the x and y coordinate of the point where the line is tangent. So I know the x coordinate is 4. I will need to find f of 4, and then f prime of 4 should be the slope. So first thing I'm going to do is find the derivative. So you might want to rewrite the function as 2x squared minus 7 to the 1/2. Some people want to find, the point first. As long as you find the point, x and y, and the slope at that point, it doesn't matter which order you do it in. I usually go the derivative route first. So I'm going to take the derivative of this. It's going to require the chain rule again. So 1/2 times 2x squared minus 7 to the negative 1/2. That is me basically applying the power rule, leaving the inside alone, times the derivative of the inside, which is what makes this obviously a chain rule, because it's 2x squared minus 7 to the 1/2, not just x to the 1/2. So I have to account for that interior piece by taking the derivative of that inside, which is 4x. So I will clean this up a little bit. So the 4x stays in the top. 2 times 2x squared minus 7 to the 1/2 moves to the bottom. You could reduce the 4 in the top and the 2 in the bottom if you wanted to. It won't change the value you find. So I have my derivative. So I'm going to find at this point f of 4 and f prime of 4. So f of 4 is going to be me plugging 4 into the original function, and what this is obviously aimed to do is find the y coordinate of the point where this line is tangent to the graph. So what you should get is 5. So f of 4 is 5. So my point 4 comma 5 is my point of tangency, and then I need to find f prime of 4, which is the slope of the tangent line. So I'm going to plug 4 into the derivative, which you should get is 16 over 10, which is 8 over 5. I'd encourage you obviously to pause this video as needed if you need to just work it out yourself and then check with what I have. It's always a good strategy, but again, you should get 8 over 5 for the slope and 4, 5 for the point. So my line should be y minus 5 equals 8/5 times x minus 4. I'm going to leave it like that. You could write it in slope-intercept form or move the 5 over if you wanted y equals. There's a couple different ways to write it, but I usually leave it in point-slope form unless I need to write it in function notation or something. For b, I'm going to do the same thing. So first I'm going to find the derivative. So the derivative of this will require the chain rule. So it'll be, notice it's some function of x all raised to some power. So it'll be 2 times that function of x to the first, leaving that 4x cubed plus 3 alone originally, and then I'm going to multiply that by the derivative of the inside. So the derivative of 4x cubed plus 3 is 12x squared. So now I have, if I wanted to simplify that a little bit, I get 24x squared times the quantity 4x cubed plus 3. That is my derivative. So what I need to find now is the y value at -1 and the derivative value at -1. So y of -1 is a way to write that, because if that was obviously f of x, I'd write f of -1, but since it's y, you could really write y of -1 and plug that in the original function, and what you should get is 1. So the point of tangency is -1, 1, and the slope at -1 would be me plugging -1 into my derivative. So notationally, you write dy dx with a vertical line is just saying I'm going to evaluate the derivative at x equals -1. So when I do that, I should get -24. So the derivative at -1, I just showed my evaluation step there, should be -24. So I have my slope and my point. So my equation of my tangent line should be y minus 1 equals -24 times the quantity x plus 1. And I would leave it like that. So still, answering similar questions, equation of tangent line, just doing it with more complicated functions that require the chain rule to take the derivative. So for example 4, I'm going to take the derivative of this function because it's asking where f of x has a horizontal tangent line. So what you need to think of for a horizontal tangent line is derivative equal to 0. So if I'm going to take the derivative of this, there's a couple ways to go about it. The way I wouldn't do it, although you could, is use the quotient rule. Most students, you see something over something, they think quotient rule, which you could use the quotient rule here for sure. The reason I wouldn't is I have a binomial over a single term denominator. So what I would do is actually rewrite f of x. So I'd split it into 2 fractions, which means my function becomes -x minus 2x to the -1st. So that's me moving that x up. And then I take the derivative here. Again, you could use the quotient rule. This one actually doesn't require the chain rule, but either way you should get the same value, same x value. So this is the way I chose to do it. So f prime of x, I could just use the power rule in both cases. So I'd get derivative of -x is -1. The derivative of -2x to the -1st would be positive 2x to the -2nd. So I might rewrite that first as -1 plus 2 over x squared. And then I'm going to set this equal to 0 and solve for x. Because again, what that'll be telling me is at what x values does this function have a horizontal tangent, which is where the derivative equals 0. So 0 is going to equal -1 plus 2 over x squared. Add 1 to both sides. I would multiply both sides by x squared here, giving me x squared equal to 2. So x is going to be plus or minus root 2. What that means is if at those x values, if I were to graph this original function, there should be tangent line that's horizontal, or obviously a slope of 0 at those values. And for the last example of the day 8 notes, we're asked to find where the following function is decreasing. So what that should say to you, hopefully, is where the first derivative is less than 0. So again, what I'm going to have to do is take the derivative, set the derivative equal to 0, using those x values that I get, make a chart and determine where the sign of the derivative is positive or negative, and in this case we're looking for where the derivative is negative, which will tell me where f is decreasing. So we'll walk through the derivative process and all that. This derivative will require a chain rule as well as a product rule. So I'm going to set up the product rule. It'll be x times the derivative of e to the negative x squared plus e to the negative x squared times the derivative of x. So that's the setup of the product rule. Haven't taken any derivatives yet. And what you should hopefully notice is to take the derivative of e to the negative x squared will require the chain rule. So what this is going to be is x times e to the negative x squared times negative 2x. And again, that's e to any power. If I take the derivative of it, it's going to be e to that power times the derivative of that power, which in this case is negative 2x, plus e to the negative x times the derivative of x, which is 1. So that is the derivative step. I'm going to have to do a little bit of algebra to get this in a form where I can solve it. So what I do is call this negative 2x squared e to the negative x squared plus e to the negative x squared. So all I did was simplify that first term. So to solve this, I'm going to eventually set it equal to 0, but I'm going to go one step further and factor out an e to the negative x squared. So now I have the derivative that's equal to a product of two things. So if I want to set this equal to 0, I would do that, and then what that'll allow me to do then is set each of these factors individually equal to 0. So set e to the negative x squared equal to 0 and negative 2x squared plus 1 equals 0. So one thing you can verify graphically if you need to is if I looked at e to the negative x squared and tried to figure out where it's equal to 0, it'll never equal 0. There's no x value you could ever plug in that if I took e to that power, it would give me 0. So there's no real solution there. It doesn't mean there's no x values at all. It just means none of my critical values will come from that factor. So then to solve the other one, I'd set 2x squared equals 1, so x is going to be plus or minus square root of 1/2. So with those two x values, I'm going to make a chart. So negative square root of 1/2, positive square root of 1/2, and I'm making a chart for the derivative. So I'm going to check values to the left of negative square root of 1/2, in between negative square root of 1/2 and square root of 1/2, and to the right. So I'm going to check, negative. You should verify that negative square root of 1/2 is about like negative 0.707. So I'm going to check like negative 1 or negative 2 or any negative number really, as long as it's less than negative 0.707. Plug that into the derivative, and what I should get is a negative number. I'm going to check 0 in between. If I plug 0 into the derivative, I should get a positive number. And if I plug something larger than square root of 1/2 in, I should get a negative number to the right of square root of 1/2. So what that means is the intervals negative infinity to negative square root of 1/2 and square root of 1/2 to infinity is where f would be decreasing. So I'm going to write that f of x is decreasing on the intervals, and I'm going to write them straight from my chart. And my reasoning would be since the derivative is less than 0 there. So in this problem, we had to obviously go through the same steps we did before, take the derivative, set it equal to 0, solve it, make a chart. The only difference is we had to use the chain rule in order to compute the derivative of this product function. So that's it for day 8. A few different types of problems that we took the derivative of. Obviously also in the same context we've been dealing with, which is concave up, concave down, increasing, decreasing, and slopes of tangent lines. So review this video, pause it as needed, make sure you can work through these problems and understand kind of the format and the setup of these derivatives, and you should be good to go for our quiz coming up.